Well, we made many egregious approximations, you might say, as we developed the LMS algorithm. As a result, you might imagine there are many more approximations that we could make, some of which make things better in terms of convergence speed and performance, and some of which make things worse but still functional. We'll first start with the ApproximateNLMS algorithm. The LMS algorithm, and I put the complex form here, is of course just a wait, update, and then the filter function. When we go to NLMS, we are simply changing the wait update, and it turns out that for nearly all LMS algorithms, we are just going to focus on this term here and come up with different wait updates which we can use. Some of them more accurate, some of them less accurate. For NLMS, as you recall, we have beta times E conjugate x of n over x, the norm squared of our x vector. I left a little space in there because it's very common to add an epsilon in there just to make sure that we never go to 0 and blow up and have a really large estimate. So this is very useful for non-stationary signals, because with a stationary signal it may be a little bit difficult but not impossible to estimate what our best mu should be. With a non-stationary signal, the optimal value of mu may change, which means you need to reevaluate what the eigenvalues are. Rather than do that, we can use the normalized LMS filter and simply choose a beta that's now appropriate across any eigenvalue range, and all we have to do then is use that beta, and the norm of x squared on the bottom is going to accommodate changing statistics of the signal. So NLMS works really well if you're doing something on MATLAB or a high-end processor. The problem is that division is actually a very difficult operation to perform. As you know, multiplication of two numbers is a lot easier than long division of two numbers. And likewise in hardware, there is no simple direct set of steps that leads you in a linear fashion to a solution with division. Rather, you have an iterative type of arrangement as you're approximating your dividing result closer and closer at each stage. In Intel processors, for example, they have a command that does an approximation, and it does it iteratively, getting closer and closer to the solution. So division takes a lot of time and a lot of work. If you're going to be implementing this in a say a DSP processor, you won't have a division function built into the processor. Everything needs to be emulated. So we want to somehow get rid of this division. This is going to be a problem. We're going to do it by doing an approximate division. First thing we'll do is we'll assume that we have some sort of floating point format for x. Turns out if we don't, that's okay, but it's easier to explain starting this way. We're going to actually assume that our norm squared of x is equal to a mantissa times 2 to an exponent. So that's a normal floating point format. The trick comes in just assuming that that's going to be approximately equal to a mantissa of 1, which isn't too far off, and that works out okay. Then 1 over the norm of x squared is approximately equal to 2 to the negative exponent. Okay, when we multiply something by, first off, that was really easy. Our division became a sign change. and this operation is implemented as simply a shift. So we're not going to implement it as a shift just like that. As long as we're making this type of an approximation, we may as well go a little bit further. And let's represent the error in the same format. Furthermore, let's approximate or constrain beta to be 2 to the minus b for some integer value of b. Then we can approximate this entire update expression as two to the power of some value here, the exponent of e minus b minus the exponent of the norm squared. So then when we multiply that by x, now we truly just have a single shift. There is no multiplication by b, there's no multiplication by the error. Everything is done as a single shift. And the best part is, this is calculated once per output sample. And it's just a shift amount. So once we have the shift amount, we go shift all the values of x by that amount and add it to w. Now, if x is in a floating point format, rather than shift the bits per se, we change the exponent of x according to what our number of bits is. I forgot one other thing. This is very important. We can't lose track of the sign of x. So let's go ahead and put that in there. We have to, or rather the sign of e, to make sure that we're moving in the correct direction. So I'm sure people have thought of this before, but I had some students working on a hardware implementation of an NLMS adaptive filter, and the division was a big hurdle, and so they came up with this idea. I don't know if they were the first or not, but we've published it, and one of the things that we did was look at how well this performed, in terms of its error. And they had to run it 1,000 times. They had to run it 1,000 times because an LMS operating normally gave a curve something like this. And when we did it with this method, we got something that looked about like that. Almost impossible to tell the difference.